Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young. Chapter 4, Harmonic Constructions and the Fundamental Theorem of Projective Geometry. Section 36, The Configuration of Pappus, Mutually Inscribed and Circumscribed Triangles. Theorem 21. If A, B, C are any three distinct points of a line L, and A', B', C' any three distinct points of another line L' meeting L, the 3 points of intersection of the pairs of lines A, B' and A', B, C' and B' C, C, A' and C' A are collinear. Assumptions A, E, and P. Proof: let the 3 points of intersection referred to in the theorem be denoted by C double prime, A double prime, B double prime, respectively. Figure 44. Let the line B double prime, C double prime meet the line B prime C in a point D, to be proved identical with A double prime. Also, let B double prime, C double prime meet L prime in A1. The line A prime B meet A C prime in B1. The line A B prime meet A prime C in B1 prime. We then have the following perspectivities. A prime C double prime B1 B is perspective with center A to A prime B1 prime B double prime C is perspective with center B prime to A1 C double prime B double prime D. By the principle of projectivity then, since in the projectivity thus established C double prime is self-corresponding, we conclude that the 3 lines A1 A prime B double prime B1 DB meet in the point C prime. Hence, D is identical with A double prime, and A double prime, B double prime, C double prime are collinear. It should be noted that the figure of the last theorem is a configuration of the symbol 9339. It is known as the configuration of Pappus. Footnote: Pappus of Alexandria lived about 340 AD. A special case of this theorem may be proved without the use of the fundamental theorem, chiefly exercise 3 of page 52. It should also be noted that this configuration may be considered as a simple plane hexagon, 6-point, inscribed in 2 intersecting lines, if the sides of such a hexagon be denoted in order by 1, 2, 3, 4, 5, 6, and if we call the sides 1 and 4 opposite, likewise the sides 2 and 5, and the sides 3 and 6, chiefly Chapter 2, Section 14. The last theorem may be stated in the following form. Corollary: if a simple hexagon be inscribed in 2 intersecting lines, the 3 pairs of opposite sides will intersect in collinear points. Footnote: in this form it is a special case of Pascal's theorem on conic sections, chiefly Theorem 3 of Chapter 5. Finally, we may note that the 9 points of the configuration of Pappus may be arranged in sets of 3, the sets forming 3 triangles, 1, 2, 3, such that 2 is inscribed in 1, 3 in 2, and 1 in 3. This observation leads to another theorem connected with the Pappus configuration. Theorem 22. If A2, B2, C2 be a triangle inscribed in a triangle A1, B1, C1, there exists a certain set of triangles, each of which is inscribed in the former and circumscribed about the latter. Assumptions A, E, and P. Footnote: the term circumscribed may be explicitly defined as follows. A simple endpoint is said to be circumscribed to another simple endpoint if there is a 1-to-1 reciprocal correspondence between the lines of the first endpoint and the points of the second, such that each line passes through its corresponding point. The second endpoint is then said to be inscribed in the first. Proof: Let A be the pencil of lines with center A1, B the pencil with center B1, and C the pencil with center C1. Figure 45. Consider the perspectivities. The pencil A is perspective with axis B2A2 to the pencil B perspective with axis B2C2 to the pencil C. In the projectivity thus established between the pencils A and C, the line A1C1 is self-corresponding. The pencils of the lines A and C are therefore perspective. Theorem 17, corollary, dual. Moreover, the axis of this perspectivity is C2A2. For the lines A1C2 and C1C2 are clearly homologous, as also the lines A1A2 and C1A2. Any three homologous lines of the perspective pencils A, B, and C then form a triangle which is circumscribed about A1, B1, C1 and inscribed in A2, B2, C2. Exercises. 1. Given a triangle ABC and two distinct points A', B', determine a point C' such that the lines AA', BB', CC' are concurrent, and also the lines AB', BC', CA' are concurrent, i.e. such that the two triangles are perspective from two different points. The two triangles are then said to be doubly perspective. 2. If two triangles ABC and A', B', C' are doubly perspective in such a way that the vertices A, B, C are homologous with A', B', C' respectively in one perspectivity and with B', C', A' respectively in the other, they will also be perspective from a third point in such a way that A, B, C are homologous respectively with C', A', B', i.e. they will be triply perspective. 3. Show that if A', B', C' are the centers of perspectivity of the triangles in exercise 2, the three triangles ABC, A', B', C', A', B', C' are so related that any two are triply perspective, the centers of perspectivity being in each case the vertices of the remaining triangle. The 9 vertices of the three triangles form the points of a configuration of Pappus. 4. Dualize exercise 3. Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.